Hello, everyone. Today we're going to be covering the ideal gas law. The ideal gas law is a combination of the four laws we discussed yesterday. So it combines all the equations together to form a new one. And what that equation is this: PV is equal to nRT. Okay. You rarely see it in this form. It's the same equation, but just the one on the right is how you're usually going to see it. Okay. And what's saying is that pressure times volume is equal to moles times R, where R is a gas constant. Okay, we'll call it a gas constant. And T is temperature. Okay, in regards to R, there are different values for R depending on what unit you have it in. Okay, what unit you're using. Okay, the one people use the most is this one right here. Okay, where volume has to be in liters, pressure has to be in atmospheres, and then you have moles, and you have to have the temperature in Kelvin. Okay. The only difference between the top one and the bottom one is that, and then is the unit of pressure. The bottom one uses kilopascals. The top one uses atmospheres. That's the only difference, and it changes the value of the number. Like I said, R changes depending on the units. So this is the number we're going to be working with. But you have to remember to always have the pressure in atmospheres, temperature is Kelvin, and volume has to be liters. Okay. So you have to keep the units consistent, otherwise it won't work. Now, what do you use the ideal gas law for? Again, you use it to make predictions. You use it to figure out, okay, what is going to be the condition of my gas after the reaction takes place. Why is that important? Okay, again, let's say we have a container. We have a metal container. The metal container can only hold so much pressure. Okay, and let's say you have a chemical reaction where you make more moles. Okay, in the gas laws from yesterday, in the gas laws from yesterday, we saw what happens when either temperature increases or moles increases. These things, there are some things that can increase your pressure. So let's say you have a chemical reaction where you're increasing your pressure at the end of it. You need to know what that pressure is going to be because you want to make sure that your container can hold it. Because if it can't, the container is going to explode. Okay. And so that's what these calculations are for. You can predict, okay, what condition is the gas going to be in after the reaction takes place to make sure that you're being safe, to make sure things don't get too hot, to make sure things don't expand too much, to make sure things don't explode. Okay. That's what these calculations are for. So you can be safe, make predictions about what's going on. Okay. Now today's going to be a fairly quick one because all you really do with this equation is you rearrange it, plug numbers in, and solve. Okay. So for example, here's a quick one. What is the temperature in Kelvin of 32 grams of a gas that occupies this much space and has a pressure of X? Okay, so they give you all the values. We're looking for temperature. So go to your equation. PV is equal to nRT. We're solving for T, so you need to rearrange it for T. You do that by dividing the N and the R, and you get your T equation. Okay. Convert your numbers, because remember I told you volume has to be in liters. Okay, they convert it to liters. You need to have moles, so they convert grams to moles, and you need to have your pressure in atmospheres, and they convert everything to atmospheres. So you have everything you need, plug your numbers in, and solve. Okay, so it's all you're really going to be doing today. Have your equation, rearrange it, solve. They plug the numbers in, they get a value, 1.3 Kelvin. Boom. Okay. I'm going to go through some examples in a second, but not with these because these are just plug and chug. This is more realistically what you're going to get. So you have a chemical equation. Again, this is called the ideal gas law. So you would use this for gases. So if you look at the chemical equation, everything in here is in gas form. G, 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 G. Everything here is a gas. So we can use the ideal gas law in this situation. Okay. So when I first studied chemistry, what always confused me is stuff like this. How can you have more moles on the right than you do on the left? How can you make, I thought things were conserved. This doesn't break conservation. Because if you remember, moles are just numbers of particles. Okay. So what's going on here is that these two reactants are being manipulated in a way that you end up with more particles. Okay, you broke it apart into more pieces, but the total mass of everything, the total mass of everything is still the same. Okay, so if you add up all the masses, it's the same on the left and on the right. Remember, it's the law of conservation of mass that needs to be withheld. Moles has nothing to do with mass. It's just the number of particles. So we end up with more particles on the right than we do on the left. That's what this is saying. And because you end up with more particles, there is going to be a change in the condition of your gas. Okay. So in this case, we go from 6 moles to 7 moles. Assuming that everything else, well, it depends on the situation. If we're keeping certain things constant, let's say we want pressure to stay the same and temperature is staying the same. There's no heat here. If we do that, then the increase in moles is going to increase our volume, let's say by 7/6. Okay. And if volume is being held constant, then pressure is going to go up and volume is going to go up. Depends on which one you're holding constant. But this is just an example. You're going from 6 moles to 7 moles, and you need to use the equation to figure out how that's going to change. Okay. And let's do an example. A reaction occurs in a flexible container. Okay, we have a flexible container. What clue or what is that telling us? Well, remember from yesterday, we used flexible containers when we were doing what? When we were keeping pressure constant. Okay, we use flexible containers when we want to keep pressure constant. Where's the one with volume and pressure? PV. Okay. We use flexible containers when we want pressure to be constant, okay, or volume. We're holding one of the things constant. It has to remain the same. So that's what that's telling us. It is going to expand to account for the pressure. There is nothing here about temperature. Okay, so let me write down the equation real quick. PV is equal to NR. That's an ugly T. Okay, PV is equal to nRT. We have an initial volume of 12. So we have 12 liters in the beginning. It says wants to know what is the new volume after the reaction below goes to completion. They don't say anything about temperature. So I'm going to assume temperature is staying the same. It doesn't talk about anything about heat. Okay. So now let's answer the question. We need to look at, well, is the equation balanced? 1P, 1P, 5 CLs, 5 CLs total. So the equation is balanced already. Okay. How many moles on the left do we have? We have 1 mole total on the left. How many moles on the right do we have? We have 2 moles of gas total. Okay, remember you just got to add up the coefficients. If there's no number, you always assume 1. So 1 plus 1 gives us 2. So when this reaction finishes, we are going to end up with double the moles that we started with. Okay, so now let's look at our equation. Again, it says flexible container, which means volume is going to increase, and we are assuming pressure is being held constant. Okay, so P is not going to change. That's the assumption we are making. So now, and temperature is also not changing. So if moles doubles, okay, so if this gets doubled times 2, what's going to happen to my volume? R is constant, T is constant, P is constant. They cannot change. This equation has an equal sign, which means the left side and the right side have to be equal. So if I'm doubling this, what do I need to do to volume to keep it the same? To keep the equation equal, I also need to double it. So the answer to this question, what is the new volume after the reaction goes to completion? It's 24 liters. Okay. Assuming we're keeping pressure constant, it doesn't say anything about temperature, so we're going to assume temperature is constant. And R is a constant by default. This is what has to happen in order to keep the equation equal, in order to keep everything valid, okay? That's the shortcut to these things. We didn't have to plug in any numbers, just based off intuition, following the math. In order for this thing to take place, this has to also be true. That's how you work out these types of problems. Okay, let's do some actual examples. Okay, the reaction below occurs at a constant temperature and volume. Okay, so let me write out PV. Everything in green is what I'm gonna. Well, everything with an arrow, green arrow on, is staying the same. That's what I'm gonna do. PV is equal to nRT. Okay, occurs at a constant temperature and volume. So temperature is not changing, volume is not changing, and R never changes. R is a constant by default. So the only things changing here is pressure and moles. It says the initial pressure is 110 kPa. What would the final pressure be after the reaction? Okay, let's count up our moles. Well, is everything balanced? Let's see. We have 2 chlorines on the left, 2 chlorines on the right, 2 carbons on the left, 2 carbons on the right, 4 hydrogens, 4 hydrogens. So the equation is balanced. Okay. How many moles are on the left? We have 2 moles on the left. How many moles on the right? We have 1 mole on the right. Remember, just add up the coefficients. Okay. So what's happening to my moles after the reaction? I'm getting half the amount of moles. I'm getting half the amount of moles. So to keep the equation equal, because remember the left side and the right side have to be equal, if moles is getting cut in half, what has to happen to my pressure to keep it equal? That also has to get cut in half. So what is my final answer? Half of 110 is 55. That's 22. Okay, how are we doing on time? Okay, 12 minutes. I'm trying to, let's aim for at least no more than 20. This reaction occurs at a constant pressure and temperature. Okay, so I'll do one more. PV is equal to nRT. Constant pressure and constant temperature. R is always constant. So the only things changing are volume and moles. Okay. The initial volume is 2.8. What would the final volume be? So same thing. How many moles do we have on the left? This is the same equation as we just did. So same thing. So 2 and 1. So again, my moles are getting cut in half after the reaction. So then to keep things consistent, the volume also has to get cut in half. So your final answer is going to be 1.4. Okay, that's how you use that. Okay. Now, some of the problems are going to say that you have conditions of STP, or standard temperature and pressure. Okay, remember when we first talked about moles, we defined what this is. Standard temperature is not room temperature. Okay, standard temperature is 0 degrees Celsius. Okay, so remember room temperature is 25 degrees Celsius. Okay, so don't confuse room temperature and standard temperature. Standard temperature is 0 degrees Celsius. Okay, which converted to Kelvin is 273. Okay, so standard temperature and pressure means 273 Kelvin and 1 atmosphere. Okay, and what volume does 1 mole of gas occupy at 1 atm and 0 degrees Celsius? Or in other words, what volume does 1 mole of gas occupy at STP? If you remember from the mole unit, we have this number already memorized. We talked about this, okay? It's always 22.4. If you're at STP and you have 1 mole of gas, it's 22.4. But if you don't remember that, you can calculate it. Okay, you can actually calculate it. PV is equal to nRT. Okay, you want to solve for volume, so then get V by itself. So you get V is equal to nRT divided by P. Okay, N is 1, we have 1 mole. T is 273, and pressure is 1 atm. Just plug in the R. R is whatever value it is in that table up top. Okay, see, I believe it was 0.08206. If you plug all these numbers in, you will get 22.4. Okay, and they demonstrate that right here. See, plug in N is 1, R is 0.08206, T is 273, 1 atm. Plug it in, you get 22.4. Okay, and that is the end of the ideal gas law section. Okay, it's just one equation. It's just practice using it. Okay, how are we doing on time? Okay, 16 minutes. So for today, this is, again, another multiple choice. There are calculations involved. I put all the information you need at the top of the worksheet. The equation is up there for you in case you forget, so you don't have to go back to the slides. I tell you R, so again, you don't have to go back to the slides. And I give you some of the conversions that you need, okay? So 1 atmosphere is equal to 760 torr. So if you look at number 1, they're looking for the temperature in Celsius. Okay, they tell you moles, they give you liters, but they give you the pressure. They give you the pressure in a unit that's not ATM. Okay, so you need to convert it first. Okay. So you have all the conversions you need. Sometimes you get millimeters of mercury. So for example, in number 4, they give you 500 millimeters of mercury. Torr and millimeters of mercury are the same thing. Okay. 1 torr is the same as 1 millimeter of mercury. There's just another word for the same thing the scientists decided to come up with. Okay. So you would use the ATM conversion to do that, since torr and millimeters of mercury are the same thing. And I tell you how to go from Kelvin to Celsius as well. Okay. Or Celsius back to Kelvin. Either way. They both go, you can rearrange it however you want. Okay. So I'll do one example in here. I'll do number 6. If you look at number 6, they want to know how many molecules. So you got to remember, to go from moles to molecules, you need to use Avogadro's number. Okay, can't forget that. Okay, so I'll do number 6 with you, and I'll leave the rest for you guys. So we want to know how many molecules are there in 4 liters of gas, 500 Celsius, and 50 torr. Okay, I'm gonna pause this real quick because I need to get my calculator. Okay, I'm back and I have my calculator. Okay, so we need to solve for moles first. If you look at the PV, well, I guess let me start from scratch so you can see that I'm not making stuff up. PV is equal to nRT. We want to solve for N because we need moles first. Before we can get molecules, we need moles. So then rearrange the equation and you get that N is equal to PV divided by RT. Okay. We have pressure, but it's in the wrong unit. Okay. It's in the wrong unit. So to go from torr to atmosphere, we need to use the conversion above. So 50 torr times, remember I showed you how to do conversions. What you're converting to goes up top. We need to go to ATM, so ATM should go up top. What you're converting from should go on the bottom. We are coming from torr, so torr goes on the bottom. And then just plug in the numbers. It's 1 for ATM and it's 760 for torr. Your torrs cancel and you're left with just ATM. Plug that into your calculator and you should get 0. I'm going to round 0.066. ATM. So that's my pressure. That is my pressure. Okay. Now I need to convert Celsius to Kelvin. To go from Celsius to Kelvin, just add 273. So this is going to be 773 Kelvin. So now I have everything I need. Plug in my numbers. Pressure is 0.066. Volume is 4 liters. R is that value up above, which is 0.08206. And temperature is 773. Plug those numbers in. You should get that N is equal to 0.066 times 4 divided by 0.08206 times 773. And we get 0.00416 moles. Okay. So that's how many moles we have. And then to go from moles to molecules, you need to multiply by Avogadro's number, okay, which is 6.02 times 10 to the power of 23. If you do that, you should get C. Okay, 2.5 times 10 to the 21. That's what you should get in your calculator after you plug those numbers. So that's number 6. That's number 6. Okay. Number 5 is just asking you what's STP. Number 4, you're looking for moles, so rearrange and solve for N. 3, you should know what 3 is. We just talked about that not that long ago. The volume of an ideal gas is 0 at blank, okay? This might be a little confusing, depends on if you remember or not. In regards to, how are we doing on time? Okay, 12, this one a little over. All right, this is, I'm a talkative human being, I'm sorry. Gas molecules move around. They have motion, okay? And that motion always gives them a volume. So the only time the volume would be 0 is if the gases aren't moving at all, okay, at all. Because remember, gases always take up the same volume as their container. And there's no such thing as a 0 volume container. No such thing as a 0 volume container. So when would a gas occupy 0 space? Remember that assumption we made about individual particles having zero, what's it called? 0 volume. Okay, individual gas particles have 0 volume. So the volume would be only 0 if the particles weren't in motion ever and didn't expand anything. So what you need to remember is which one of those answers is absolute 0, because things stop moving at absolute 0. Okay, there's a slide on here that shows you that. Okay, so you just have to remember which one of those answers is the temperature of absolute 0. Okay, that's what you gotta know. Okay, which one of those is absolute 0? Okay, but that's it for today, everybody. Take care, be safe, and have a good one.